Good morning, everyone, or perhaps good afternoon if you're joining from a not European location. And we would like to welcome you to our webinar. Okay, that's me, in case you didn't know how I look like. And I hope you can see our screen. So today, as Justina mentioned, we're gonna show you some advantages of how you can use atomic force microscopy to look at the polymers, in particular, and mostly Teflon, and how you can assess the structure of those polymers down to a single molecule. So I will also show you some live measurements and give you ideas how you can do that type of measurements on Park Systems AFM. In particular, we will focus on large sample NX20 atomic force microscope, and I will show you some live measurements in a few moments. So let's start with the very simple question. Why do we need AFM for polymer science? Seems like kind of a simple question, and there are quite a few very good reasons why atomic force microscopy is extremely helpful in assessing your polymer samples. First, it provides you with a real space imaging. What does that mean? It means you can see molecules and the structure of your surfaces as they are. By comparison, in various diffraction techniques, you always get data in reciprocal space, and you have to build certain models to get an idea what the structure looks like. And that's how our structural studies of polymer have been carried out for decades, really. With the atomic force microscopy, or in general the scanning probe microscopy, you can get a real space data where you can see molecules, and in my view that's a lot more exciting. Then you can do a real-time and real space dynamics. So not only you can see the molecules, you can see those molecules acting or reacting to the external stimuli, for instance temperature, light, radiation, and so on. Another fundamental advantage of atomic force microscopy is that is a highly localized technique, and that is because you're using an ultra-sharp probe with the tip radius typically down to a few nanometers, sometimes even less. It could be much more if you're doing some functional imaging, but in principle, it is a very small probe that samples your surface. So you get an information from a rather small area on your sample, and it could be as small as a few nanometers, really, and we'll show you exactly that. Then another exciting advantage of that technique is it's not diffraction limited. So unlike techniques, microscopical techniques based on interaction of light with the, or I'd say electromagnetic radiation with the matter, it's always diffraction limited. Whereas with the atomic force microscopy, that sort of limit doesn't even exist. So in principle, that type of technique, depending on the equipment and depending on how you do it, you can go down to seeing atoms in molecules on certain systems, and that has been demonstrated. It is also a damage-free technique, so you don't need to destroy your sample to get an idea of the structure. So you can assess everything from extremely soft and delicate biopolymers all the way to very hard crystalline surfaces. So again, any sample pretty much. And apart from structural imaging, the fundamental advantage of that technique is that you can always measure some property. You can do what we call functional imaging. So you can access things like nanomechanics. So you can probe whether your surface or your sample is stiff or soft. You can probe electrical properties. You can see whether your sample is conductive, and you can measure that conductivity. So you can measure the current or resistivity of the sample, and again, on extremely small scale. You can do piezoelectric materials, and you can measure piezoelectric response from these materials again. And as Justina mentioned, we will cover all these topics in the upcoming webinars. In the meantime, we had a very good webinar on nanomechanical measurements of polymer blends. That was presented a couple of months ago by Abdul Rauf, our application scientist, and you can watch that webinar on our website. So before we proceed to the actual data, let's talk a bit about the structure of polymers, and especially about the crystallinity in polymers. If we take a polymer chain, it's usually, again, dependent on the polymer and polymer weight. It's a really long line. You can imagine it just like a spaghetti line in your plate, really. Some polymers, they do exist in such form, and a very good example is DNA, imaging mica, for instance, forming either loops or just single strands. And that's something that does happen in polymer science, that some polymers that do exist as a single chains on the surfaces, for instance. But what happens a lot more often, and that is true for many polymers, they do form folded chains with loops, and that's like a theoretical sketch that you always see in the textbooks. And that you can see in things like, for instance, the image on the left. This one is polymers crystallizing two-dimensional materials, for instance. In this instance, that's polyteflon chains on hexagonal boron nitride. So that's a rather complicated semiconductor polymer. You can see individual chains here arranged in a two-dimensional island with the thickness of just one molecule. But equally, you can see that kind of loops on top of the surface of a real real polymers. For instance, here we have a very nice image of polypropylene folded chain on top of the polypropylene lamella. So you can actually follow the molecular chain. Here's the loop. Now the polymer chain goes that way, then another loop, and so on. And from that image, we see that the structure, the three-dimensional structure of the polymer is a bit more complicated than just a loop. And that brings us to a very important concept in the polymer science, is a polymer lamella. And that's how polymers usually crystallize. They form so-called lamellas. And lamellae, you can imagine it as a sort of three-dimensional looped chain. And they form that kind of crystalline regions, and those regions interact with each other, and then you get some disordered or sort of semi-ordered or amorphous regions where those chains have no any particular order. And here's a very good example again of a isotactic polypropylene, some type of polymer that you use in your everyday life. And I sort of highlighted the region here with the red square, showing you where the lamella is. Well, actually, the entire lamella is like a long structure, but you can clearly see molecules and small loops, and they're coming in and out, and so on. And that shows you that those textbook examples are actually real. That's how the polymers indeed crystallize, and you can actually observe that with the polymers. What's important here on this slide is dimensions. When it comes to folded polymer chains, the interchain distance between those lines is usually on the order of between 4 to around about 10 angstroms. I think one of the smallest interchain distances for polyethylene, I believe about 4.3 angstroms or so. And then depending on the polymer structure, it can go a bit higher. For instance, for folded loops of the polytithene, it has 1.2 nanometers, and so on. Again, with the lamellas, the typical size and thickness of a lamella is on the order of tens of nanometers, so an order of magnitude away from the interchain distance. So it's very important to remember that kind of numbers, because that gives you a very clear idea that to get those structures and to visualize those structures, you need a really high resolution imaging techniques that allow you to actually measure that kind of small distances. And that's why AFM is extremely powerful technique. So you can see them, and then you can make some conclusion about the polymer structure and so on. So despite all these great advantages, the progress in atomic force microscopy and imaging polymers has been somehow limited, and it took a very long while to get to a point where such measurements are routine. So perhaps we should give a brief historical overview with the I believe the first routine technique where you can get that type of resolution was torsional tapping AFM that was introduced by Nick Mullen and Jamie Hobbs from University of Sheffield here in the UK. And that was the first great example of polyethylene lamella imaged with that technique, where you could observe both the single chains of polyethylene as well as molecular defects in those lamellas, and obviously nice structure of the lamella edge. That was a great technique, it still is, although it requires some special cantilevers, a T-shaped cantilevers with a sharp probe, which are not exactly cheap to buy. Then there was introduction of bimodal tapping imaging by Roger Proch, and that was published a few years ago in ACS Nano, where they observed again polyethylene lamellas forming loops and so on. The other technique that was introduced a couple of years ago is so-called higher eigenmode imaging, and that's the first example of that technique applied to polymers. And in this instance, there was polytithene, that was semi-crystalline polytithene that was imaged, and you could see CH3 groups that forms the surface of the of that polymer. But as I showed you previously, we can equally use that technique on different types of polymer. In that instance, here's an example of isotactic polypropylene, and you can see polymer chains separated by about 1 nanometer distance. You can see nice loops, for instance, here, and the previous image I showed you on the previous slides. And that's obviously it's not limited to polymers. It could be used on many other different samples and so on. In brief, that technique that we are going to talk today about is based on the fact that you use not the first or the fundamental eigenmode of your cantilever, as you often do with any atomic force microscope, but you use high eigenmodes. For instance, if we take a standard silicon cantilever, in this instance MOF 75 ALG from budget sensors, you can excite as many as, I believe, about 5 different eigenmodes. So the fundamental one is always located around about 75, hence the name. Then you have the second one that usually appears around 430 kilohertz. The third one at around 1.2 megahertz, and the fourth at 2.2, and so on. And you can excite those eigenmodes on your Park NX20 or NX10 AFMs with no problems. And the interesting thing about those different eigenmodes, they provide you a slightly different shape of the cantilever oscillation. For instance, here we show you what roughly the shape of the fundamental eigenmode looks like. So it's basically like a hammer, goes up and down and so on. When you go to the third one, and do forgive me my sort of clumsy sketch, but that's roughly what the shape of that oscillation looks like. And the important bit here is that the actual part that oscillates is a very small fraction of that cantilever, the last, I believe, about 20% or so. So effectively a very long cantilever, and in an instance the cantilever is about 200 microns long or so. The actual bit that moves there is another something like 20 or 30 microns or so. So we effectively turn in a very large cantilever into a very small one, and increasing the effective spring constant to several hundreds of newtons per meter. So effectively that probe acts as a very stiff probe. And the beauty of that is that you can actually use very small amplitudes, and that's the key to obtaining high resolution imaging. Another great advantages of that technique is that you do not need any special cantilevers. You can use whatever cantilevers you prefer. So all of them have high eigenmodes, again, depending on your microscope or cantilevers you use. You do not need any special hardware. There's no any special software. It's all the same. So it's all the same NX20 or NX10 AFM. You don't need any upgrades. Unlike, for instance, bimodal type, where you need to buy an extra piece of software to run. It works great in both air and liquid, so there is no any requirement for any different environment. And it works great on both soft and hard samples. So we can use very soft things like we're going to show today on a Teflon, which is a very soft polymer, and you can go in a hard crystalline surfaces and get atomic lattices and so on. So so today we're going to talk about that technique, and now I'll switch to our Smart Scan software to show you some live imaging. I hope it's still running. Let me change the screen to. I hope I can see the screen. Justin, if you could confirm that you can see the right screen.
Yes, all good.
Yep, thank you. Okay, so here's an example. We're sitting right on top of the Teflon Lamellae. I will explain a bit more what exactly we're saying in the slides, but that's a typical phase image. I deliberately didn't optimize the imaging conditions, so it's like your average high resolution phase image. In this instance, it's a 20 by 20 nanometer scan, and you can see lines running along the image. Those lines, they're separated by 5.6 angstroms, and these are individual single Teflon chains. So now again, the contrast is a bit better, because with the scan and probe techniques, the image quality slightly varies from image to image, because we're talking about extremely small length scales here. If you think about what we're saying, the distance between line is 5.6 angstroms, but the full width of the half maximum of that line, which gives you roughly the idea of the width of the molecule, is only around about 2.5 angstroms or so. And to put into perspective, carbon bond, the distance between two carbon atoms, is 1.5 angstroms, and the width here that we are measuring is 2.5. So we are indeed measuring extremely small distances, and we measure them quite nicely. Of course, when it comes to getting images for publications, you might need to have a bit better quality depending on what journal you want to send it to, and that requires some image optimization. And our Smart Scan software gives you a full arsenal of tools how to optimize your imaging and get the best possible images. That I will show you in the slides what the best possible images look like. Here I can give you an idea of what you can do to optimize your imaging and get it slightly better. There are various factors that affect that type of imaging, and critical factors are your probe. That is the most important part of the microscope. Quite often people kind of forget about that, but you need to treat that. You need to know how to choose the probe, and you need to treat the probe very gently. They're very sort of delicate silicon devices, and you need to make sure that you don't heat your surface too hard, so that you maintain their sharpness. Then let me slightly reposition the scan, because we're drifting on the edge of the lamella. It's a small drift of a couple of nanometers. And here I'll show you how you can move. For instance, you can drag that window around and click scan. And here we go. We're getting again those lines. You can actually see the periodic structure of the image here in the traces. So for instance, that window shows you both trace and retrace for the phase, and it shows a very nice periodic structure. So if you were to open the image and measure the peak-to-peak distances, you'll get that 5.6 angstrom distance between those peaks. And I'll explain you why it is 5.6 and how does it compare to other techniques. Go into image optimization. There are a couple of things that you want to think about when optimizing imaging. First, if you take small scans, and in this instance like 20 by 20 nanometer scan, you need to go fast. Okay, no matter how good your microscope is, there's always a drift. There's some thermal drift that is inevitable. It could be very low, like in this instance, where you maybe have a, I don't know, that's been scanned for a couple of hours now, maybe a nanometer, 2 nanometers drift or so. That does happen, especially on the large sample microscopes like NX20, which I will show you at the end of that presentation, what it looks like. It's actually a quite big microscope. So speed is critical. So in this instance, we're scanning 8 Hertz, meaning we're taking 8 lines per second. Then another critical parameter is your oscillation amplitude. So that, as I said earlier, is quite critical that you select appropriate one, and we can use very small amplitudes. In this instance, we're using amplitude of about 2.7 nanometers to resolve those chains. That way you can adjust the, for instance, if you set that amplitude a bit low, meaning you will apply greater force, slightly greater force to your sample, you might lose the resolution. I do not know, but there's always an optimal amplitude that you need for a particular sample and for particular molecules to resolve, and that's something you need to find out in your experiment. That is one of the key parameters. Okay, now we can let that thing scan in, and we can always go back to that. And I will talk a bit more about Teflon and explain you what we're saying, and so on. In the meantime, if there are any questions about live imaging, you may ask them now, or if there are any now, just in May, let me say. But excuse me. In the meantime, I will switch into presentation. Let's go to Teflon. So Teflon, or the official chemical name, is polytetrafluoroethylene. Teflon is a commercial name patented by DuPont many decades ago. Okay, so the chemical structure of Teflon is very simple. It's effectively it's a fluorinated polymer where you have nothing but carbon and fluorine atoms. So here's the chemical structure showing the polymer chain, and that motif repeats many times, and that forms a polymeric chain. You obviously have end groups depending on how you synthesize that polymer. It could be hydroxyl or sulfonic acid, and so on. The Teflon is a semi-crystalline polymer, and its structure has been really well studied over many years by diffraction techniques. And people established that it has 4 different phases, and their existence depends on the temperature. So room temperature that we are now usually exists in the phase, I forgot, it's either phase 2 or 4, but anyway, that phase has those dimensions. So the molecules are packed in that sort of hexagonal unit with the chain-to-chain distance of 5.66 angstroms. That's what X-ray diffraction technique tells us. So that's for the bulk polymer. So for bulk polymer, they established that that kind of molecular arrangement exists. If you remember what we were seeing in the live images, that's pretty much the same, 5.6 angstroms. And that polymer is extremely well used pretty much everywhere. You're probably very well familiar with the so-called Gore-Tex membrane, or expandable polytetrafluoroethylene that is used for all sorts of waterproof jackets, shoes, boots, you name it. Probably everyone has something with the Gore-Tex. The other pretty common household item is a PTFE tape, or plumber's tape, and it is actually what we are imaging today, and what I'm going to be showing in the images in the next slides. It's just a regular tape that you can buy in any supermarket, and it's used for sealing pipes, joints, and I don't know, anything really. So nothing really special about the sample that we're looking at. So no sample preparation as such. So you can, if you have access to atomic force microscope, I do suggest you to take a piece of Teflon tape and give it a go. If you're using Park Systems AFM, drop us an email if you want to learn or have some questions or problems imaging it. We will help you with that. But it's really good fun taking a piece of polymer that you can buy in the supermarket and actually see molecules on that polymer. Okay, well, let's go to molecules. Right, before we go, that's an optical image that you can always collect, and I always advise people to collect an optical image of your sample to get an idea where you took a scan and what your sample looks like on a sort of large scale. It's always a very good idea to do that. And Park NX20 provides you with a high-resolution camera, and you can get very nice images from your sample, like with a regular optical microscope, and that's a great thing to have. Okay, Let's start with our big scan sizes. As I said before, the beauty of the atomic force microscope, it's a highly localized measurements. You can take images of various sizes depending on your scanner size. In this instance, it's a 100 micron scan, and it already reveals quite a lot of information about the structure of a polymer. We can see densely packed areas and some rope-like structures connected them, and so on. And that's pretty much your typical Teflon tape. So no matter where you go in the sample, you will get that type of image. That's your height imaging, from which you can get an idea of the topography of the height features and so on. You can always collect a so-called phase image that provides you with a bit more extra information. In a way, you can look at the image as a semi-quantitative friction map or some kind of chemical map, and so on. And if you look carefully, you probably notice that all those structures are aligned in one sort of direction, and that's actually the orientation of the tape, because the Teflon tape is oriented. It's an oriented polymer. Let's look into that region here, okay, here we go. Here we go. Here we have two more phase images. This time it's a 1 micron scan and 250 by 250 nanometer scans. Both scans, as you can see, provides you with a lot more details. Even on a micron scan, you can see that the surface is very rich in all sorts of structures, and there's all sorts of things you can observe and you can point your tip at. And that's the beauty of atomic force microscopy. You can move your probe, select the area of interest, point your probe where you want, and measure the structure or properties. Okay. Well, in this instance, for instance, here we see a very large sort of flat lamella. That's where we were scanning live when I showed you before. So and that sort of flat regions. But if you focus on the regions with the bit more texture, you can resolve again a bit more. You can actually see crystalline areas here, and those areas are connected by some disordered areas, amorphous region. And if you remember what I talked about, when I talked about the crystalline structure of polymers, that's exactly the case. You have a crystalline lamellas that interact with each other, and they interact through some amorphous regions in between them, and that gives polymers their properties like that you can expand them, their flexibility and things like that. Okay, so fundamentally, we can actually very easily get a beautiful images showing two types of region, crystalline and amorphous region on the polymer. But let's go to the actual molecules. If we take a much smaller scan, in this instance, a 100 by 100 nanometer scan, we can see those individual lamellas. Those you can see with a beautifully arrange sort of steps and so on. And if you zoom further, take a phase image, in that instance 40 by 40 nanometer scan, you can see lines. You can see lines on top of those lamellas, and when you take a bit closer look, you can see those lines a lot clearer. That's exactly what we saw live. And the beauty of the AFM images, you can take measurements. You can measure distances between those lines, and that is critical because it's not the pretty image you want to take. You want actually to get some numbers, and in this instance, these numbers are distances. So the distance between those peaks, so the average is 5.6 angstroms. And if you remember the data that I showed you from X-ray diffraction that is well known and published, that is precisely the same number, 5.6 angstrom. Although X-ray diffraction gives you a slightly higher sort of precision, and give you 5.66, I think. With the AFM, it's a bit probably less. But nevertheless, we get a very nice periodic structure seeing all these molecules. And what, for instance, techniques like X-ray diffraction, electron diffraction won't show you is the disordered regions. For instance, here we can see how the molecules from the highly ordered crystalline area enter another area, but they enter through that disordered region, and you can almost make these molecules in between two lamellas. And that, again, the beauty of the atomic force microscopy. You're not limited only to crystalline areas. You can actually resolve things within the amorphous region and get a better understanding of how polymers fold and arrange themselves in amorphous areas as well. Okay, let's have a look at another example of, yeah, by the way, if you overlay some molecules on top, that gives you an idea which way the molecules are oriented. So that's the direction of the Teflon molecule, and again, that's the distance between them. In fact, if you measure the full width at half maximum, those peaks, it gives you an idea of sort of what kind of resolution you can get. And in this instance, it's about 2.3 angstroms. So if you think about that, we're just resolving and seeing features with almost like angstrom precision in ambient with no any extra control. Okay, let's look at the lamella structure, and right, here's another area on the same tape, a slightly larger scan, 80 by 80, but that is taken with the higher pixel count, so you can see it kind of may appear slightly different depending on what screen you're looking at. That's one of the problems, I guess, of showing images, but there are lines on top of those images, and if you take a cross section again as we did before, you can get the same measurement, 5.6 angstrom difference. And interesting, if you look at the edges of those lamellas, you can see molecules coming out of those edges. Okay, and you can even see molecules underneath there on the second layer. So let's take a closer look at this particular area. So again, we see the lines, or we see molecules as we now know. And here is the edge of the other lamella. Then there's an interesting question: how are the molecules oriented into different layers? For instance, if we look at that edge, and you can see the sort of tiny molecules sticking out. Let's take a zoom and make a very simple visual experiment. We can overlay blue lines on top of the top molecules and the red line on top of the bottom ones, and we can see that those two are interdigitated. That gives you an idea how they actually packed in the crystal, in the Teflon crystal. Okay, right. To summarize, we can clearly tell that using that technique, using the high eigenmodes of the regular cantilevers on an NX20 or NX10 AFM gives us a very good resolution. In fact, we can achieve a true molecular resolution in both crystalline and amorphous region of the polymers, revealing single polymer chains. On a sample that just like a regular Teflon sample that isn't even prepared for the type of imaging at all. And crucially, we provide the same level of, almost the same level of precision as you can get from the diffraction data. You can measure the same 5.6 angstrom molecule to molecule separation or lattice constant that you can get from the bulk techniques. And that is important. That gives you a confidence that the atomic force microscopy provides you with the data that you can cross-correlate with other techniques, and that's important when you actually look, when you want to take a broader picture on the samples that you investigate. Okay, so at the end, I would like to thank you for attending and listening. And we also wish you all the best and good health, and trying to keep safe in this, excuse me, these strange times. If you have any questions, please do ask, and we'll be more than happy to answer either now, or you can forward your questions to our email address, or book any live session with us if you require a live demo, or you're interested in that kind of techniques, or are looking at your polymers with that sort of resolution. We will be very happy to guide you and help you with that. In the meantime, we can I can switch back into the and we'll let it scan, and now we will be happy to take your questions, please. Thank you.